Hey guys, um, so there are a few reasons I chose to make this video. So first, I didn't upload for a while, and a few people were asking if I'm going to upload, and it's not because I wasn't doing any contests or I was even trying to make screencasts. However, it was just was not working out. I couldn't concentrate on an actual contest that I was doing, and was distracted too much, and so I was like, at some point I would get frustrated and just turn the recording out. Yeah, but I still wanted to upload something, and I was also recently into watching videos of some guy solving puzzles, like Sudoku puzzles and stuff. And he usually does it like really quick, like 3 times faster than I could ever do. And he's really good at explaining things. So that made me kind of understand why people want to watch these kind of videos. And yeah, so I get up and I wanted to record something. So, but yeah, as I said, it's not really working as of late. Like if I do actual contest online with everyone, so I thought I would record my practice on some contest, and yeah, for a change, I thought I would solve some kind of contest that's easier than usual, like Division 1 Code Forces run or a Coder Grant contest or something like that. So I would choose a regular contest in a coder that I didn't do. So this is the contest I've chosen, KEYENCE Programming Contest. I'm not going to press myself for time and try to solve this as fast as possible. I'll try to go like reasonably fast, but I won't be doing virtual contest. It's just solving problems. Yup. And I'll try to explain, since I won't be pressing myself for time, I'll try to explain things as I go, right? With pictures, hopefully. Okay, so yeah, since this is an easier contest, if you're a top participant, then it's probably not going to be very interesting to watch. If you are, if you think that this is like some of these problems you're interested in how you could solve, and it's not obvious to you how to solve all the problems, then what I suggest to you is it's like from that puzzle videos thing that I've been doing. I would open the puzzle and I would try to solve it before I watch the video, and then, well, if I don't solve it, then maybe I can start the video and pick up some techniques and stuff, and just see how the guy is doing that. So what I suggest to you is I'm going to be solving problems in order. And before I start a problem, you can pause the video and try to solve the problem yourself. And then, well, if you can do it, you can see if I did that any differently, or like if there is a technique that I used to make it faster. If you can't solve it for quite some time, then you can kind of watch me doing that. So that's the whole idea. Hopefully it's like, since this is an easier contest, maybe more of you can learn from something like that compared to the harder contests, right, where the threshold is very high. Okay, so let's just go. Let's try to solve the problems. Okay, so we have the first problem. If you want to read the problems for yourself, there's a link in the description to the contest, and you have them on screen, so you can pause and read with me. Okay, so we have a grid, right? And we can paint something. So we can paint either a row completely black or a column completely black. And we need to have some number of black squares in the grid, at least n. So how many operations do we need to make? All right, so let's think about it. This is quite an easy problem, right? So if you want to solve, if it's not obvious to you how to solve it, pause and try to solve it for yourself before I go to explaining this. Right, so we have this grid, right? It has H rows, W columns. So in one operation, what's the best we can do? What's the largest number of squares, of black squares we can have after one operation? Well, we can either paint a row in black, right, or a column in black, in which case we get either H black squares or W black squares. So the best we can do on the first turn is the largest of H and W. Okay, so if this is at least n, then we are done, and the answer is 1. So if this is not enough, what's the best we can do on the next step? Right, so we can go with, for example, we chose row, right? So W. We could either go with the, and yeah, since we went with the row, it was the case that W is at least H, right? Because we chose optimally. So on the second step, we could either go for another row for another W cells, or we could go for a column, which you can see gives us less black squares than it used to. It now gives us H minus 1. All right, so we have a choice between W new squares or H minus 1. Okay, but on the first turn, we chose W because it was larger, and out of these two numbers, this is only smaller, so W is still larger. Okay, so in 2 steps, it's optimal to color another row, and you can see it's the general thing. Since rows are better than columns, then it's always better to take rows, because first of all, they are like at least as large as columns, and also as we take more rows, the columns get like progressively worse. Okay, so after k turns, the number of black squares we can have is k times largest of H and W. All right, and we need to have at least n of them, so this has to be at least n. Okay, so in fact, since this is the number of squares we have after each operation, then k is equal to n over maximum of W, H and W rounded up. So I guess this is just a simple formula. I hope I didn't misunderstand that. So for the first sample, it appears to work, right? So 10, and the largest is 7, and 10 over 7 rounded up is 2. Here, it's not that obvious. 120, let's bring up the calculator, over 18. Okay, so that's just 8, and 8 rounded up is 8. And here, we of course choose 100. Okay, so that's like, takes just a hot minute to solve. Okay, so we read the numbers and then we output something. Okay, so we want to output n. Let me introduce this variable. So we want to output something that's n over s rounded up. Okay. How do we do that? Like, if you're not familiar, this is something that appears a lot. Like, how do you, for example, if we wanted to round down, we would output just n over s. Okay, so that would be n over s rounded down, because that's how C++ works. But if we want to round it up, okay, there are a few tricks we can do. We can check if n is divisible by s, and if it is, then this is just the answer. If it isn't, then this plus 1 is just the answer. But the trick you can do, like whenever I solve this, whenever I need to use this ceiling of n over s, this formula just works. If it's not clear why it works, like take a moment and see if you can spot it, if you can prove it. In most cases, an even simpler formula works, like that. So that is n over s rounded up as well. In most cases, okay, this does not work. This may not work in n is equal to 0 because of because of the way how the rounding for division works if you use negative numbers. So in C++, it's a bit tricky. In our case, n is not equal to 0, I hope. No, okay. So hopefully this is just the answer. Let's actually test it, since we have the time. That took a long time to compile. Okay. 3, 7, and 10 should be 2, right? Okay, so this is 2. Cool. Let's try and submit that. Nah, it's still judging. Let's go to the next problems. I have, okay, so that works, right? So that was an easy problem. You would kind of expect a problem like that at the start of a problem set if it's like kind of division 2 contest, if you know what I mean, like division 2 code versus or at code regular. A lot of these problems are simple formulas, which still can take some time to like figure out why this the formula is true. So all right, so let's go to the second problem. Again, if you want to solve it for yourself, go ahead and pause the video and get back to me when you're done with trying to solve it. All right, so we have n robots in some coordinates, in different coordinates. It can sort of extend their arms. Okay, so what that means is so that means is the problem statement is we have some, basically we have endpoints, right? For each robot. So each range looks like this, basically. We don't exactly care, like we can just think of these as a set of segments. We don't exactly care about this. Let's just talk about left and right endpoints. Okay, and out of these set of segments, we want to choose as many as possible so that they do not intersect, I think. All right, so that's kind of a classical problem. Like when you're starting to learn sort of easy scan line and greedy and sorting, that's a problem that you're very likely to encounter. Okay, so let's consider all our segments, and in when we are picking segments with restrictions to like intersections and stuff, usually what we do is we sort them by increasing of their right coordinate. If they have equal coordinates, then I don't think we care that much if they have equal. Yeah, the order doesn't matter. Okay, so let's order them. Okay, so now out of these, we choose some of the segments so they cannot intersect. All right. So which is the first one? Which is the first segment in our order that we can pick? We argue that that can always be the first one. Why? Because if we didn't choose it, let's consider, for example, this one. This segment is the first one, but it does not intersect with anything, so all other segments start later than the end of this segment, right? And so it won't hurt us to get rid of this segment and instead take this one, because its right endpoint is only to the left. Okay. So yeah, this segment we can always include in the answer. Cool. What's the next one that we can include? Let's so we go from left to right. These, okay, we cannot take. These we cannot take. Oh, this way, this one we can take, because it does not intersect with the previous one. And well, in fact, the new problem, what's the next segment we can take after this one, is the same problem if we get rid of all the segments that intersect with the first one. All right. So what that means is this is the first one that does not intersect with the previous one. Right. The same is true for the next one. Like think it through. This is now the last segment, the first segment that we took. We can ignore everything before it, and we can again get rid of anything after that, and then we take the first one, right? And these steps repeat. They are kind of independent, and like, yeah, you can try to do these steps in like repeatedly, one after another, maybe erase the segments and so on, but you can you can achieve the same thing if you just sort segments by its right endpoint. So RE is right endpoint. Consider all segments from left to right. By increasing, right? And then we just take segments greedily. So this is sort of exactly the same that we were doing, right? We would take a segment as long as it's possible. So if it does not intersect with the previous one. Yep. So we just sort, and then we go over the segments and take them. Yeah, that's sort of a classical problem. It took me longer to understand what the statement said than to recognize that it's a classical problem. Okay. So we have these segments, right? Let's read them. In fact, we don't care about X and L. As I said, we only care about the endpoints. So we want to sort them. In my template, PII stands for a pair of two integers. Let me find it. Yeah. Okay. So So we need to have n segments. Let's read them. This just iterates from 0 to n-1. Okay, so we have x and o. Okay, so then we would have to sort them by right endpoint, right? So how do we do that? This is basically the same thing as, okay, so just sort by increasing or by lexicographically by the pairs, but that would sort by increasing of the left coordinate, and that's not what we want. So one dirty trick that you can do is to make, so this is a pair of two integers, right? Let's make the first element of the pair the right endpoint and the second one the left endpoint. We don't care about the order anyway, as long as we remember what everything means. You can still do it in the original order, but then you would have to sort by a non-standard comparator. This you can do, for example, by plugging a lambda function here. So this is a lambda function that compares to pairs, and it puts, so this one returns true if A should be put before B, and that happens if the right endpoint of the first one is to the left of the second one. So like that. I'm trying to avoid using my usual shortcuts so that it's clear. Yeah, any of these ways will work, but as you can see, the second one is just a little bit longer to do. So I would usually go for the first one. Cool. So now we have to keep track of how many segments we've put, and to greedily take the segments, we want to keep track of the last right endpoint that we've took. Okay, so for example, somewhere at this stage for this segment, we would have to keep track of this endpoint here. Okay. Initially, we don't have any segments, so we can just put it to a very small number. Okay. And then we have to see if this can be taken. So a small detail that is maybe easy to miss, that segments do not include the endpoints, right? So they can be equal. We can take a segment with left endpoint equal to R if this is R. Okay. If it was not the case, then this would have to be greater than R. Okay, so these corner cases you have to be wary of them. Okay, so the left endpoint should be at least R. What do we do in this case? First of all, we put this into the answer, so the answer is increased by 1, and also R is the left endpoint of our segment. In the other case, well, we cannot do anything, because yeah, we just cannot do. Right, so that pretty much completes the problem. So we read, we sort, and we take the segments greedily. Cool. So let's try to run some of the samples here. So the answer, we have a warning, which usually means that I forgot to read the n, which is it wouldn't work. Okay, so 3 is what we have, and it seems to be correct. So this is 1. This is 5. Okay, so with simple problems, with really simple problems, you are tempted to this takes like 1 or 2 minutes to type in, well, or maybe slightly longer, but anyway, it's tempting to just submit the program after that. But as you can see, if I would submit it, I would get the wrong answer because I forgot to read "and." And so I usually test all the problems before I submit. It's not worth it to go fast at this particular moment. Okay, so let's submit that. We don't need this. Maybe we go to the next problem. So did we solve it? So it runs. Yeah, looks like we're all right. Cool. So the next problem, again, pause if you want to solve it for yourself. All right. We need to construct an array of positive integers so that exactly k pairs sum up to s. So let's think about it. So we're concerned with these ranges that sum up to s. Okay, so there could be one of these ranges. The other one, like if there is another one, cannot. The ranges that sum up to s clearly cannot be contained in each other, because the range would be so if this is s, this would be larger than s. Okay, so what that means is the ranges kind of always move to the left. Okay. So there can be at most n of them. And we have a constraint of k is at most n. Okay. But then we can just one case is when all these ranges are just one element. So if we place k copies of s, then each of these is going to be a good range, right? Because the sum is right. All the others have to be something other than s. So for example, s plus 1 would work. Okay, so s plus 1 cannot be contained in any good range with some s. So all of the rest can be s plus 1. So we have these k ranges of s, and that's exactly what we want, right? This should work. So let's look at the constraints here. We have, okay, so the numbers that we can place cannot exceed 10 to the 9th. Okay, so what happens is if s is 10 to the 9th, the number s plus 1 would exceed our limit. So in this case, the solution works unless s is equal to 10 to the 9th. So we have to kind of treat it specially. If s is 10 to the 9th, then instead of s plus 1, we can just use 1s, right? Because 1s are so small compared to s that there cannot be a range large enough so that the sum would be 10 to the 9th. Okay, so all right, so we have n, k, and s. So we have to output k copies of s, and then n minus k copies of some other number, which is either s plus 1 or 1. Let's say that this number is t. Okay, So if s is equal 10 to the 9th, then this is 1. Otherwise it's s plus 1. Okay, so this ternary operator, if this expression is true, then it's equal, it is resolved to something other after the question mark. Otherwise it's after the semicolon. If I wanted to write cleaner code, you would go with if s is equal to this, t is equal to 1. Otherwise t is equal to s plus 1. It's exactly the same thing. Okay, so now we have to output k copies of s and then n minus k copies of t. This is a shortcut, another shortcut that I use for a cycle. This is the same as, you can see the it's defined over here. This is the same thing as this. It's just a shorthand that is like, you can see it's like 3 times shorter, so that's what I usually use. Okay, so we have to output k copies of s and then n minus k copies of t. And then we carry the line. You can see that like the line with the answer is going to end with a space if you output it this way, but usually the checkers are lax enough, so you don't have to care about extra spaces or line breaks that you put in your code. So that's just simple. Okay. It's going to be a different answer, of course, but you can see that it's kind of something that we want to do. Right, so it does, the special case is treated correctly, I think. There are other ways to solve this problem, but this is kind of free. If you came up with a different solution, then great job. Either way, it's like if the solution would turn up like harder than I would expect, I would spend some time and simplify that. But in this case, it's not really necessary. Okay, so 3 problems down. Let's go to problem D. Maybe at some point they're going to be harder. Maybe this contest is just too easy. Anyway, I hope the last few problems are going to be interesting. Okay, so we have cards. Okay, 2 numbers on different sides of each card with red numbers facing up. Okay. Interesting. So this is kind of a interesting process. Let's see. N is small. Okay. All right. So let's see. So the process that we have is, so we have these numbers, the cards, right? So one side of the card has some number AI, and the other is BI. Okay, so what we can do is, like, initially AIs are shown on the top of the card. What we can do is we can swap 2 adjacent cards and also flip them so that it would show a different number. So if it showed AI, it would swap to BI. or the other way around. And the question is, can we have a non-decreasing sequence of numbers regardless of the colors? What should we output? Okay, so the smallest number of operations. All right, so that's something that's not like solved immediately, at least by me. Right, so at any point we have some of the cards facing up. Some of them are red and some of them are blue. And if for each card we decide if it's red or blue, then it's kind of there's a single way to arrange them, almost, because we could have equal numbers, right? So what I'm talking about, if the numbers are fixed, so we have chosen for each card if it's going to be red or blue at the end, like which number is going to be shown. Okay, so then there is almost a unique order in which these cards can go. So this would be 2, 3, 4, 7, as long as there are no equal numbers. And equal numbers can be like these two cards can go in either order. But we also, if we figure it out, like which is which, we can also see that the number of blue cards is always even, because each operation, it's like either takes 2 red cards, transform them into 2 blue cards, or it's the other way around, or it's right blue to blue red. You can see that in either case, the parity of the blue cards is preserved. It's either the same number or it's changed by 2. So that's the other observation. Okay, so n is small. We probably need some kind of 2 to the n solution, so some kind of dynamic programming. Right. We cannot like the easy solution would be to like consider all possible permutations and colorings, but that's a bit too large. Should be an easy problem, right? How exactly do we do that? So if we swap 2 cards, they become in inversion, and also, so by inversion I mean they are not in the same order as before, and their color is flipped. Ah, okay. So what we can notice is for each card, so let's say we have a card I. Let's swap it with card I+1. So initially this card is red, for example, or it's like now it's red. Okay, so we swap it with I plus 1. We can look at the number of inversions for my tablet. Miss B, hello? Don't do that. So we can look at the number of inversions for I, which is the number of other cards J, so that I and J are not in the same order as originally. So if I was before J in the original order, then now it's after J, or vice versa. So how many cards are like relatively shuffled with respect to each other? We can see that how does the number of inversions change for I? It does not change its relative position with anything other than the card I plus 1. And I plus 1, if it was an inversion, it's not an inversion anymore. And if it is an inversion, if it's not an inversion, now it is an inversion, because I and I plus 1 swap the order. And so that means that each operation changes this number, more specifically changes its parity. Parity is changed after each operation, right? But also the colors change simultaneously. The colors change at the same time the parity of inversion is changed, right? So that means that if the color of the card in the final configuration is red, then the number of inversions changed an even number of times. And if it's blue, it changed an odd number of times. So if it's red, we made an even number of operations with it. And if it's blue, it changed an odd number of operations. But what also changes simultaneously with the number with the parity, it's even simpler. The position, the parity of the position of this card changes. So if the card, what I mean by that is that, for example, hello. If the card started at position 3 and it was red, each time it moves, it flips. So if it ends up on positions 2 or 4, it has to be blue, because the number of operations that was applied to it is even. And if it ends up at position 1, it should be red again. And this is pretty much the only constraint we have, right? Because as long as for every card, if for every card the finishing position and the starting position have the same parity difference as indicated by R and B, then everything is good, because no matter how this card gets from 3 to say 1, it's still going to be all right. It's going to be red anyway. It could go right for some time, then it could go left. Regardless of how this card ends up at 1, it's still going to be red. That's much simpler than the parity idea that I had before. It's much simpler than that. Okay, so with that knowledge, how do we solve the problem? we can try to do dynamic programming. So basically, so let's say that we place card from right to left, right? And we have this set S of cards that are still unused. Okay, so all cards other than S are placed here in some order. Okay, so which card is going to be placed next? Also assume that we know this card. Okay, so which card is going to be placed next? If this position is I, then for each card, if some other card J from S is going to go to I, then we know if it's going to be red or blue, because if I and J have the same parity, then there is going to be an even number of flips, and it's going to be red. Otherwise, it's going to be blue. And so this is enough to determine if any card can be placed here. So dynamic programming of, I think, I and S is right. So now we have to minimize the number of operations, right? This we can do by noticing that each card should travel independently some distance, right? So, for example, if this card goes 3 to the left, then it has to take part in like 3 operations, at least 3 operations, because it could go right and then it could go left. And so we have like, this has, for example, 3 steps to make, this has 8 steps to make, this has, I don't know, 6 steps to make. But each operation, like, it works towards making at most 2 of this useful step. So the number of operations to achieve the goal is the sum of all these numbers rounded to, divided by 2. It's at least this number, right? We cannot make less than this because it won't be enough to make all the steps. So this is at least 7. And in fact, it's exactly 7. And this we can prove by showing that there is always a pair of cards we can swap, and so both of these steps are actually going to be useful. So all the cards go towards their destinations. I don't even know how to prove it off the top of my head. Like, if I think for a minute, I will know. But maybe it's going to be useful if you try to prove it on your own. Why can we always solve the problem in like exactly this number of steps? The number of steps each card has to make over 2, right? So what all that means is, instead of minimizing the number of operations, we can minimize the total distance that has to be traveled by all the cards. Okay, so what's the dynamic programming is going to be? It's the minimum total distance for all the cards that we have placed before. If the last card is I, the last card we've placed with is I, and the unused cards are in set S. Okay, so the next step is going to be check, try to all numbers in S, try all J in S, try to place it after I, look at the parities, figure out if the sequence is still non-decreasing, and then add something to the answer, like relax some of the values. I'll try to explain as I write the code. Hello. All right. So VI stands for vector of integers. It's another shorthand. So now the code is getting more complicated. I'm going to use my shorthands. Okay, so first of all we read A's and then we read B's. Okay, so for dynamic programming we need this array. One dimension is up to n and the other is up to 2 to the nth, like that. Okay, before we do anything, we want to initialize the array with infinities because we don't have any information yet. For example, 10 to the 8th. All right, so then we initialize. Okay, so instead of s, I'm going to be storing the complement of s, right? So which numbers are used already. Okay. So if the first number is I, then the set of used has only one bit I. The bit operations, right, with mask. So this is 1 shifted down n bits. So this is 2 to the nth, and so this number is the number that only has I in its bit representation. So this way we encode the sets. Right, so this is the same as the set of positions of ones. So counting from left to right, starting from 0, that would be the set 1, 2, and 4. Okay, and so if we only want to have a set that contains I, then the number has to have the only one in bit I. So that's 2 to the power of I. Okay. So this is equal to the distance of the card I traveling to the very first position. All right. So now what we do is we consider all cases by increasing of the mask, rather by decrease of use numbers. All right, of use numbers. So it has to increase. Okay, so what I'm going to write is this. It's important that like the order is exactly this, because otherwise we could reach some of the states before all the transitions leading to the states were resolved. Okay. So something like this. Okay, so now let's figure out. So we have let's figure out what the next position is. Okay, so the next position is the number of bits in mask, right? So the position here, this position P, it's the same as the number of cards that we've used before. Well, if we count from 0. Okay, so how do we count the number of bits in mask? There are a few ways to do that, with a cycle or something like that. If you're using G++, you can call this function. That's like kind of kind of a gray area. It does not exist in the C++ standard, but it works in G++. Okay, so now we place the card at position P. Knowing this, we can figure out, so the previous position is P minus 1. By using that, we can figure out what's written on the previous card. If the position of I and the position, and if I and P minus 1 have the same parity, then the card I has to be read. Okay, so let's try to work this out. We know that this card is the card I, like this. Let's try the other one. Okay. No, don't do that. Okay. So the last card we've placed is I. This is the card that's like either AI or BI. No, stop doing that. How do I? All right. So and its position is P minus 1. So by our previous discussion, if I and P minus 1 have the same parity, then the card reached the position P minus 1 in red state. So it has AI. Otherwise it has BI. Okay, so let's put this down. If I modulo 2 is equal to P minus 1 modulo 2, then we should have AI. Otherwise we should have BI. Okay. So now let's try all options of the other card. Of the card that goes immediately after that. So this is the card J. Okay. So the card J cannot be present in our set of used cards. Okay. So the Jth bit cannot be 1. In this case, we don't go into the cycle at all. So how this works, if we want to check if this is 0, but if we shift mask J bits to the right, then this is the same as 0th bit of mask shifted by J. Okay, if it's 1, and the 0th bit can be checked by just by taking and 1, right? So if in this case we go forward, in the other case, let's figure out what's written on the card J that goes in this position. We can use exactly the same trick by taking this formula and replacing I with J. Let's say that the next number is Y. We can just replace I with J and P with P minus 1. So as I'm putting together this horrible code, if you are any kind of decent like developer and all, you may be just getting chills from how ugly this code is. We're going fast, right? We're trying to do things here. So if I were to work for you or whatever, I wouldn't write the code this ugly, but then I probably wouldn't be solving these kind of problems anyway. All right, so if y is less than x, so it goes x and then y. If y is less than x, then we continue. In other case, let's figure out what's the next state we end up in. All right, so the last card is now J. The set of used cards is the old set, but also it now includes the card J. So we do it like this, right? We unite the sets, so that's bitwise OR. Okay. So the new minimum distance that we can have is dp. It's our old dp I mask plus the number of steps the card J needs to make to get to position P, which is the difference between J and P. Okay. So then we would take this value, compare it to D. If it's larger, then we put it equal to D. I have this to continue with terrible shorthands. This is something that I use to. So when I write U in of this and D, it does exactly that. If this is larger than D, then it gets decreased to D. If it's smaller to D than D, then it does not do anything. Okay. So with that, we're done with dynamic programming. So what's the answer? Initially, it's infinity, and then we have to consider all options of the last card. Okay. And using U in the same way. So the last state, we should have all cards used. Right, so the last card was I, and also all of the cards were used. That means like the set of all numbers from 0 to n minus 1 corresponds to the mask 1, 2 to the n minus 1. Okay, like that. All right. It could also be the case then that we don't have an answer. Minus 1, for example, is like, it could be that there is no answer, in which case our answer is going to just be infinity. Right. So if answer is large, so there are like, if either answer is infinity or it's some small number like 100. In fact, answer is twice the number, if you remember correctly. So if answer is like large enough, then it's clearly infinity. So the actual value that we need to output is minus 1. Otherwise, it's twice the number of operations. So we divide it by 2, and this should be the value that we output. So that looks right. See, again, it's the same warning and it's the same error. I didn't read the N. Right. Shouldn't do that. Okay, so let's input here. I'm not sure what's going on here. I think we should make one operation. Yeah, the answer is 1. Here, I believe there is no answer. Okay, here the array is already sorted. Cool. Here there is no answer for some complicated reason. And here you should make 3 operations. Well, that worked. Right. So the constraints, let's submit it. I was just thinking if, like, these take a little bit to explain, and it's like, it's this kind of dynamic programming. I don't personally love it all that much. Maybe there's, but then again, how would you solve this problem differently? Oh, we have a wrong answer. We have a wrong answer. Very nice. We get to look for errors. Let's Anyway, as I was saying, what was I saying again? We're looking for... Right, we're looking for the error. So the initialization seems correct to me. If the first card is I, it has to move to position 0. This is the number of used cards, so P is the first position that we need to place, and the previous one was P minus 1. Okay, this does not work correctly if mask is 0, but these cases do not actually do anything. Alright, so if J is used, we don't do anything. Y is what we place based on the parity from the card J. It moves from position J to position P. So this is our distance. If answer is large, we should output -1. If answer is small, ostensibly that's... Maybe we have like... How many cases have we missed? Are actually quite a lot. Actually quite a lot. And also all of them are big. No, not all of them are big. I'm not going to look at them, but so we've read the numbers in correct order at least. N is equal to 1. That should like automatically work, right? Not sure what we're missing here. Maybe n is equal to 1 gives us some trouble. Doesn't seem like it. So in this case it's 0. In this case it's, oh, it's the sample case. In this case it's probably 1, right? Interesting. Okay, it's not true. It's not true what I said. It's not true about the sum of the distances. It's not true. It's just not. How would you go about changing 1 to 3 into 3 to 1 in 2 operations? Shut up. How do you do that? The sum of distances is 2. Well, it's 4. So we argue that the answer is 2. It was not true. The entire solution is just wrong. Yeah, I shouldn't have gone on. I'll try to be clever and say, oh yeah, that's an easy like exercise for the reader. Maybe you should like. That's what happens when you don't pay attention to justifying your solutions. You just get eliminated. Some of the time. Sometimes it's fine, but so it's not the dynamic programming, and I don't see a way. To maybe our yes, actually, maybe our initial idea with the number of inversions worked. Yes, see, this has 3 inversions and this has 0 inversions. So the answer is, in fact, 3. But then how do we account for the fact that, oh yeah, so the number of inversions, instead of the distance, let's keep track of number of inversions. Right, so for example, we have arranged, shut up. So for example, we have arranged some of the numbers in this first part, right? So what we want to keep track of is how many, so these are indices of the cards. So how many pairs among these are not in order? And so if we place any old number, if we place any old number here, then knowing this set is enough to update the number of inversions. Okay. So what should we, instead of this, what should we add? The number of bits of mask that are larger than j. There are a few ways to do that. I'm going to go with this. If j is moved right j positions, then the only bits remaining are the ones that used to be at positions larger than j. So maybe that's the only fix we need, actually. Not quite. Oh, okay, so we don't need to have anything here anymore. All right. So in this case, if we want to put the numbers in the other order, I don't know, maybe we can do it like that. The answer is 1 because we can swap these two guys, and if this is large, and the answer is 2. Yeah, I think that worked. Okay, luckily, I'm not going to jump the gun here, and now before bragging, we actually see what the verdict is, right? Hopefully. Okay, so this looks better. Very nice. Yeah, so don't know what to say. You you have to be rigorous about your solutions, is I guess the outtake, because otherwise you can just lose a whole lot of progress. Like in the worst cases, it takes up the entire contest because you go forward with the wrong idea, and then if it's wrong, you have to figure out that it's wrong, which takes really long time sometimes. You have to figure out how to fix it, and then maybe like re-implement everything that you've done before. Okay, so this was kind of a nice problem because the structure of, like, if you just look at the description of the operations, it's not really clear. You have to look for these different kinds of invariants. Like you have to figure out quite a lot of different things, like how the color behaves depending on how the cards move, and the parities and inversions, and how to compute the answer. But in the end, it's like pretty simple and standard subset dynamic programming, which is, yeah, it appears a lot. If you're not really familiar with that, and you are at a level where you hope to consistently solve a problem like at this position, position D in division 2 rounds, this is a good, like, there are lots of problems you can practice with. even in cut forces and lots of other places too. Okay, so we have the last two problems have conspicuously similar names, but they don't look the same. Okay, so let's go with the first one. Bichromization. So that's like making it two colored, I think. Okay, so we have a graph. Also some numbers. We want to color vertices and assign weights to edges. Okay, so at least one vertex is white and at least one is black. And the closest distance to a vertex of different color is GV. So to put that in simpler terms, if my pen does not fail on me this time, so we have a graph, right? I don't know, like that. We have something that's called GV for each vertex. We want to color all the vertices white or black, and also put numbers on the edges. Okay, so for example, this is white, and this is black. So now for this vertex, we are looking, for example, I don't know, this is a 4. This is 3. Okay, so for this vertex, after we've colored everything, it's white. So we're looking for the closest vertex that is black, and that would be so this is 6, this is 6, this is 5. Okay, so this should be equal to 5. Very nice. So we don't know what's the closest. We don't know what's the closest the closest vertex to each one, because we haven't colored it yet, and it also depends on length of the edges. If only one vertex is black, right? We make only one vertex black. Then what we have, if for example vertex 1 is black and everything else is white, let's consider this case. Okay, so this is G1. Then the numbers here are just distances towards the first vertex. So that's not really always possible to do. For example, if we have a path and G2 is 5, but G3 is, I don't know, 2, this is white, this is black, this is black, then there is no way that this is closer to the vertex 1 than this. So this construction does not always work. Maybe a different one could work. So at first I'm like thinking similar to how in problem C with sub-array sum. There was a simple form that solution has. So maybe we can have an answer like that in this problem, is what I'm thinking. It's like the range of possibilities is very large. So maybe we don't need to explore all of that to find the answer. So the first attempt didn't work. Okay. So let's look at, so we have these numbers, right? G1, Gn. I'm very cross with my pen. Why does it do that? Sorry for that. Maybe I can just. Okay. So what's the smallest number that we have among these m? For example, it's 1. Okay. So the smallest number is just the closest distance between the black vertex and the white vertex among all possible pairs. Okay, so this corresponds to a pair which is actually connected with an edge, isn't it? Because if it's not a direct path, then there is a vertex, like intermediate vertex, but if it's black, it's closer to the white, to this one. If it's white, if it's black, it's closer to this one. So this must in fact be a direct connection between these two guys. But also, so this corresponds to dv for this vertex, because it's just the closest possible distance you can have between black and white. But also, it has to be present in this vertex. Again, because we have this distance, and there is no way we can have anything smaller than that. So the smallest number have to occur at least twice in our given sequence, which is kind of cool, I guess. Yeah, look, in this case, it's not the case, and there is no answer. In this case, it's true. Okay. So how do we use that? We can. There has to be an edge, so that. So the distance, the length of this edge is equal to numbers in both of the guys, in both of the endpoints. And all of them are smallest. Both of them are smallest. All right, so we can look for this edge. Let's see how we can use that. Okay, so this is like the minimum number ever, and so this edge must have weight equal to dv. All right, so now these are kind of satisfied. These vertices do not need anything anymore. So what's next? So we can kind of sort of erase this, sort of erase the edge. Yeah, this edge is not very helpful. I mean, no, okay, it is helpful actually. Right, so there are some edges over here, and my pen. Okay, let me try to fix it before while I'm thinking about this problem. So there are some edges that leave the vertex here. What does it mean? If they're all black, if the endpoints of these guys are black, then it's not necessarily the shortest path still. Okay, I'm missing something here. Do we have any additional constraints? Okay, so now we found this edge. Maybe now we can do anything we want. Not really, I don't think so. We found one edge. What if we look at the next smallest? If you look at the next smallest number, it can always be connected to one of these guys. Maybe, maybe not. Where's my... Maybe it's all right. So what do we want to do here? The structure of the graph is kind of constrains us a lot, because like a lot of simple answers are made impossible by how the graph looks. So we kind of, similar to this construction, we kind of want to go by increasing of GV. So in the graph, we would first consider the smallest one, and then it would have, they have an adjacent counterpart, sort of. So we can call those, and we can put some numbers here. Right, so now what? Yeah, this is sort of what happened a lot to me during the actual contest. It's like I'm in a different mindset than when I usually solve the contest without the recording. So when that happens, I usually take a short break, go off the camera, think a little bit to myself. Maybe an idea comes to me. I hope you all, I hope you understand. Just skip the video a few minutes forward before I come back. Maybe you can try to think with me on this problem, because I don't have a clue still. I have to think a little bit. Okay, so I'll be back. All right, so maybe I have an idea now. It sort of generalizes what we've done before. So let's look at our vertex. So it has dv, it has some neighbors. The first observation is, let's look at the case when all our neighbors are larger than dv. Okay, so all the neighbors have larger distances than our vertex. But we argue that in this case, there is no answer. Why? Well, let's look at, so for example, this is black. So let's look at the path to the closest white vertex. It could be one of these, it could be some other guy, but this path has to start somewhere and it has to go to one of the neighbors. Okay, but then this neighbor, regardless of its color, it either has if it's black, then it has a path to this white vertex that's shorter than dv, but it has distance larger than dv, so that's not possible. If it's white, then it has path to, if it's white, then it has path to this white vertex, which again is shorter than dv. So this cannot happen. This can never happen. If a vertex has all neighbors with distances larger than itself, then the answer is just not possible. Okay, so this case is ruled out. The other case if one of the neighbors is smaller or equal to dv. Okay. So now let's think about the length of the edges. Let's initially put all length to be infinities. All right. So let's look at this neighbor. If it's also dv, and so what we can do, if it's like so for example, this is the smallest neighbor, okay? So this is the smallest neighbor. So this is and it has the same number as us, okay? So what we can do is we can color these differently, and then both of these guys are going to be satisfied, and all of the other guys, well, let's just not care about them for a moment. The other case if both of these are if there is a guy that's less than dv, that's the other case. What we can try and do then is have this colored the same, and here we can put the difference between the colors, between the distances of this vertex and this du, for example. And so if this is satisfied, if this has a path to a white vertex of his length, then this vertex is also going to be satisfied. And all of the edges we consider to be infinities. So if we don't put anything to any of the other edges, the vertex is smaller than this, then this is going to be satisfied as well, right? So yes, that seems to be all right, but it's not very rigorous yet, because we kind of know what to do in each particular case, but is it going to be consistent in the end? So what we want to do is let's look at let's look at the entire graph now. And we want to consider vertices in groups with the same dv, with the same value d. Okay, and we do that by increasing of d. Okay, so first we consider all vertices with the smallest d, and let's consider only edges between such vertices. So there are some edges, and my pen misbehaves again. I still haven't fixed it. I know what to do. Let me try to fix my pen before I go forward. Let me reapply the nib real quick. Please bear with me as I do this. It's going to take just a short moment. Okay, so let's reapply that. Okay, seems better now. So we're considering edges between all the vertices with the shortest d. So what do we do in our algorithm? Our algorithm would consider all these vertices. Let me see if the mic is working. Oh no, it's still, the pen still does weird things. Anyway, so let's look at all the edges, and what our algorithm is going to do, it's going to try to color these vertices differently. So for example, we can choose any spanning tree of this sort of subgraph on smallest vertices, and then it would color vertices of this spanning tree alternately, and put all the weights equal to d. So for example, this is a spanning tree. So we color vertices alternately, okay, and put all weights equal to d. So what this does is all the vertices have, they all are now satisfied, right? There could be multiple components, but we can just process them separately. Okay, and all other edges are assumed to be infinities, so they just don't do anything. We put infinities towards them. Okay, so this gets rid of all the small vertices. So let's consider the next group. Say the next value is d strike. Okay, if this is connected to one of the smaller vertices, so if it has a smaller neighbor, what we do, so for example, it's this neighbor is smaller, then what we do is we give it the same color, but the edge here is going to have the weight equal to the difference. And so this vertex is now also satisfied because this was satisfied, and all the other edges are going to be infinities. Supposedly they're going to be infinities. Yes, and then for all the vertices gstrike, we kind of do the same thing. We take the spanning trees on all vertices with gstrike, and then we choose the spanning tree, we color them alternately, and yeah, we put gstrikes here. I'm thinking, do we actually have to do this? Do we actually, in this case, if there is a component, then we don't actually need this edge. So the only case when we need this edge, if there are no neighbors equal to our gstrike. Okay, so we don't do that. We don't do that. If there is a neighbor with an equal gstrike. So the only case is when this procedure will not put anything is when some of the neighbors are smaller than dv and some of the neighbors are larger than dv. In which case, this is kind of an isolated component. And so what we do then is we choose any neighbor that's smaller than us, and we put the difference on the edge. Okay, so now all the vertices are kind of two types. Either they have the same neighbor, in which case they are going to be resolved by this procedure with taking components and doing stuff. The only vertices that are not going to be resolved are of this type. But in this case, they're going to be resolved by looking at the smaller neighbor, any smaller neighbor, and coloring it the same as this smaller neighbor, and putting the difference on the edge. And so assuming that this was resolved, this is going to be resolved as well. Right, so that's probably what we should do. Okay, so I hope the solution is clear by now. Yes. So how do we implement that? So now instead of groups, let's consider just all vertices V by increasing vertices V by increasing of dv. Okay. So it's either part of a group of connected dvs with the same value. And so let's say that if we find a vertex of a group, we just start coloring the adjacent ones with the GFS. Okay, so if V is uncolored, then start a DFS at V that only uses that only goes to vertices with the same value dv, and what it does is it applies dv to all the edges between these vertices, and only in the spanning tree, and the vertices are colored alternately in the spanning tree, right? So if the first one is black, then its neighbors are all white. If this one is white, then its all neighbors are black in the spanning tree. Then its all neighbors are white, and so on. So that would resolve the entire component. And so we won't have to run the DFS for any of these vertices anymore. So the first one in the component will see the DFS. Okay, but we only do that if there is a neighbor with the same DV. Okay, exists a neighbor. If there is not a neighbor, then we look at all adjacent vertices, and there has to be one U, a neighbor U, so that GU is less than GV. In which case, we copy the color and the length of the edge between V and U is put to be dV minus du. Okay, so since we are going by increasing of dV and color everything we meet, then du has to be colored, so we can copy the color. And yes, the only edge that all the edges with V adjacent to V are still not have the weights. So this is going to work. I think that's going to work. Okay, so let's now try and implement that. That took a really, really long time. Okay, so we're getting to problems with some kind of serious implementation and graph algorithms and so on. Okay, so let's introduce some graph stuff. And so this is the size of arrays for vertices. So what are the arrays? The order of edges is kind of important here. The order of edges is important. So usually we would say that each vertex, so this is how I would usually go about implementing the graph. So EV is list of neighbors. This is usually enough, but we also need to care about numbers of edges because we want to color them and stuff, right? So instead of this is going to be a list of pairs, which is neighbor and ID of the edge. Okay, so that makes this the list of pairs. We also need to store the weights for the edges, and this array needs to be slightly larger than that. Give me a second. I'm going to sneeze. Okay. What we also need is an array of colors. So let's say that -1 is uncolored, 0 is black, 1 is white. This is initially infinity, and let's say that our infinity is the largest possible weight, and the largest possible weight is, I think, 10 to the 9th. Okay, right. What else do we need? I don't think we also need the G's. That's just given to us. Okay, so we do something and then we output the colors and then we output the edges. So that should be quite enough. That should be quite enough. So let's read the data first. So we read N and M. Then we need to read these with my usual shorthands. Then we need to read the edges. Okay. So U and V are connected. We also want to change the numbering. So the vertices here are numbered from 1. So let's decrease all the indices by 1. Okay. So now we know, and also indices of the edges are going to be from 1. Okay. So now we need to add the new edge in both directions. So U now has a new neighbor, a new edge that leads to V and has index I. And the same goes from V. Cool. So now we've filled all our data, and we also have to initialize some of our arrays. So initially all of the edges have to be infinity, and also all of the vertices have to be uncolored. That's -1. Alright, so now we want to process vertices by increasing of their D. How do we do that? Here's how I usually go about it. So this vector is going to be the order of vertices that we process them in. We have to fill it with numbers from 0 to n-1 in some order, and this is sort of the function that does it. Okay, so now we need to sort this by increasing of D. Here's how we are going to do that. So we use the standard sort function with a custom comparison, and this is going to be again a lambda function. I use this a lot, and like if you're not familiar with it, maybe you can do some other stuff. You can use something else, but this is kind of short and convenient, so I'm using this. Okay, so this is the custom comparison, and V comes before U if D is smaller. Okay, so now this vector, the order, contains all the vertices in the order we want to process them. So we want to iterate V in over all elements of the arrays in order, and here's how we can do this in like sort of not completely archaic standards. This is a cycle that's going to work. Okay, so this iterates V from left to right in the vector. It only works for vectors, it doesn't work for arrays. So okay, so now we have these two cases, right? These two cases. If there is a neighbor, or there is not a neighbor. So let's try to find the neighbor. So we iterate over all edges. So this edge leads to U. Okay, so if G of U is equal to G of V, then we have a neighbor. Okay, so now if there is a neighbor, then we are in this connected component, right, like this. Either this component was already colored. If this is colored, then we already have a color as well. So if this is not -1, then we don't have to do anything, we just continue. Okay, otherwise we've just arrived at the component and we need to run some kind of DFS. So this DFS starts coloring from V, and V has to have color 0. So let's write this GFS now. Okay, so we start DFS from V, and C is the color that we put towards this vertex. Right, so what the DFS does. So it considers this edge to a neighbor. If the neighbor has a different D, then it's not in the component, so we don't have to do anything. If the neighbor is already colored, it means that the edge is not in the spanning tree. So we don't have to do anything as well. Otherwise, we want to run the DFS to U, and this flips the color. If C was 0, then this is 1. If C is 1, then this is 0. So this works out nicely. Okay, so I think it does it for this case. Right. Otherwise, if there is not a neighbor, then we want to look for an adjacent neighbor. Like this case, you probably can't follow this, but we're looking for a neighbor with a smaller marking. So let's say that this neighbor is X. Initially we didn't find it, so let's put it to -1 to mark that we didn't yet find it. So we iterate over our neighbors again. So this is our neighbor. Oh, in the GFS, we forgot to color the edges, right? So in this case, we have to color the edge between V and U. We need to put the edge to it to be equal to, so the weight of this edge, which is given by its index, which is the second element of the pair. It just has to be dV, right? Right. Okay. So this now does everything we want in the GFS part. Here, if d of u is less than d of v, then we just put x to be equal to u. As a matter of fact, let's just store the entire edge. Okay. So this is an edge that leads to a smaller neighbor. And initially it's -1. Okay. So smaller edge is just equal to edge. Okay. We don't care about which exact edge it's going to be, as long as it's smaller. Now, it could be that we didn't find this edge. In this case, this is -1. So what happens here? If that happens, then we don't have a smaller neighbor, we don't have an equal neighbor, so all neighbors are larger, and we figured that this cannot happen. Okay, so we will introduce a global flag that's true if everything is okay, and in this case it's not okay, and we can just end the entire procedure because there is no answer. Right. Otherwise, we take this smaller edge, and let's say that its other end is u. Okay. So d of so we have to copy the color from this guy, right? So we follow this part here. So we copy the color, and edge is the difference. The weight of the edge is the difference. Okay, so the ID of the edge is this second element, and this should be equal to the difference. And that's pretty much it, I think. Yes. Alright, so now we've done everything we want. If everything is not okay, then there is no answer. And I think we have to print -1. Yes, so let's print -1. In the other case, we want to output colors, so blacks or whites. We've colored all the vertices. It doesn't matter which one is black and which is white. We also, yes, it's important that we have at least one vertex of each color, because there has to be at least one component of equal G's, and these have at least 2 colors, so that's okay. So let's output the colors first. So col of E is the color, and here's how we can output this. Again, it's nasty code, but this is 0 or 1. This is a string, and this outputs the character of this string with index col. So it's 0, it's going to output black. If it's 1, it's going to output white. It's just a shorthand that I use. You don't have to use that. You can put a condition there or something. Okay, and then we output the weights, and this is just W, I think. That probably does it. Cool. So let's see if it works at all. So it outputs something. I'm not sure if it works. We can try to draw it out, since it's I really want to be sure that this works on this sample. Okay, so we have edges from 1 to 2, from 1 to 3, from 3 to 2, from 4 to 2, and from 4 to 5. Okay. Why does it do that? Please don't do that. Okay, so this is 1, 3, 2, 4, 5. The G's have to be, this is 3, this is 3, this is 4, this is 5, this is 7, I think. Okay, so this is the first vertex, this is the third one, this is the second one, the fourth and the fifth. Right, so what does our algorithm do? It says this vertex is black, all the others are white. Also, the weight of the edge 1, 2 is infinity. This is infinity. All right. 1, 3 is 3. 3, 4 is, no, 3, 2. 3, 2 is 1. And then this is 1 and this is 2. And you can see that this works nicely because yes, it's like this has closest 3 here, and all of these have to follow this path here. Right, so this was the component that was processed first, and these were just single vertices with smaller neighbors. All right, so what do we have here? This is the case when the answer does not exist, and I think it should be relatively easy to solve. All right, so what happens here? We have a complete graph, and all vertices have to be at distance 1 from a vertex of a different color. So what this does is it paints edges 1, 2 to 3 and 3, 4. It puts weights 1 on them, and it also colors them alternately. Yes, and this works nicely. So I think this should be it. Okay, so this was not an easy problem, I have to say. You have to be, And I think that if you take some shortcuts in uncovering the exact construction, then it's going to it can go bad, really, because if you miss some of the cases, then it's like it's hard to figure out why exactly the solution does not work. Okay, maybe there is a solution with a smaller number of cases, but I'm not sure, because it's like if you try to go around some of the cases, then you can like we've avoided some caveats here with edges that have to have weight 0, for example, that we cannot do. So maybe these can be a problem. All right, so I think we're 2 hours in. We've solved most of the problems, and we are past the time limit for the contest, but we're just taking our time. We're just chilling. So the last problem, let's try to solve the last problem. If we want to solve it for yourself, pause it, think about it, and then let's see if we can solve it together. Okay, so we have the grid again, and again all squares are painted white and black. Okay, so we know the paintings, we know the colors. Maybe not. Do we know? Oh, okay, so we have some operations too. Okay, so we have the initial sort of the starting configurations, and then we can apply some operations to that, which is choose a row or a column and then paint everything in there either white or black. Okay, so we can only apply some operations to we can only repaint the old colors as many times as we want. Okay, so with these kind of problems, what you usually look at is the last operation you make, right? So the last operation you make, which one is it? It could be that there are no operations at all, in which case we just have the initial state, whatever it is. Some cells are painted. Otherwise, let's consider what was the last operation here. For example, it was a column here, so it's either white or it's black. And if it's white, it's going to be white no matter. It's going to be white no matter happened to these cells before. So all of these are white or black. If it's painted black, then it's all black, and it doesn't matter what happened to these cells before. In fact, if you look at all the last operations that are of the same type, so if we choose a row or a column, so let's look at the last operations that are columns, right? So it doesn't matter in which order we apply them, and all of them are going to overrule the old colors, whatever they were. So what we can do now is we can sort of forget about all these columns and only treat the rest of the board here and see how many colors we have there. Okay, then we can look at the rows, this part, but there's we could do that, like consider a subset of rows and subset of columns. And do some sort of dynamic programming on that, but it has like sort of a larger overarching problem with it, and that's double counting, because for example, let's look at this grid. It has this row, this column black, and also this row black. All right, this is the final configuration, for example. And so if you consider the last operations to be rows, then this may be our choice. Okay, so we can say, so we go with rows last and then columns before that, and then we say, so okay, this row was painted black and then this column was painted black before that. But it could go the other way around too. It could be this column and this row. So these are two separate ways in our sort of solution. It doesn't count the colorings that we can obtain. It counts the operations, and that's not what we want to do. So maybe we need to be a bit more careful with that. Right. So we can, so this, in the final configurations, in different final configurations that we can look at, the order, like, not the order, but unbroken rows and unbroken columns are somewhat important. You can see what I mean. These can only be, the last operations can only happen in these rows or columns, right? So let's look at final configuration, and let's look at all the unbroken rows and unbroken columns. So there are, if there are no unbroken rows and unbroken columns, then there are no operations could be made, and so the only case when it could happen if the state is initial one, right? If we do have unbroken rows or unbroken columns, if there is if some of them are black and some of them are white, then they cannot intersect, since all of them have to be unbroken. And so either we only have unbroken rows, unbroken columns, or unbroken rows. Some of them are white, some of them are black. Okay, so this now is better than what we had before, because now we can say that all of these have to be unbroken. All of these have to be unbroken, and that uniquely maps to the colorings, so that's better. It doesn't double count anything. So in this case, if these are unbroken and all the others are, well, not unbroken, what we can do is we can say there is a sequence of operations that potentially leads to that, is to paint these columns and erase them and treat everything else as the independent part of the board, right? So now we have these smaller independent states that's obtained by erasing some rows, and then later maybe some columns too. But we also have the condition, if we did that, that none of the columns can be unbroken. So only rows can be unbroken now. And if no rows are unbroken, then we couldn't do anything to this configuration from the start. So the remaining cells, after cutting out these rows, cannot be touched by any operations. And so they must be the same as the original board. And we know what it is. Right. So we have this intermediate state where now columns can be unbroken. Now columns can be unbroken. Right. There is another case. So in this case, we had both black and white columns. We could also have black and white rows, which would lead to a symmetrical state. But we could also have the case where we have some unbroken rows and columns, but all of them are the same color. So for example, there are some rows that are black, and there are some columns that are black, and there can also be some rows that are black, some subset of them. Okay, so at this point we can erase both of them, and that leads us to another state which says that no row and no column can be completely black, because if it was completely black, then we had to erase it on the previous step. Okay, so that's the general idea we follow. We look at the final configuration, we look at the set of unbroken rows and columns. This is uniquely determined for each final configuration. And then we have some of the conditions. So every final configurations can be sort of uniquely unraveled by a sequence like this. Right, so from this case, where there are rows and columns of different colors, we go to this state with a restriction that no column is unbroken. From this, what can we do? We cannot have unbroken columns, so either the state is final or we have unbroken rows, in which case we take all the unbroken rows and the remaining rows cannot be unbroken. But we have to take care. We have to take care because we have to satisfy the condition of unbroken columns too, and sometimes this is not exactly possible. For example, if in this configuration we say that all rows are unbroken, this also means that all columns are unbroken too, because everything is the same color. Where does that put us? So that's tricky. There are a lot of cases and there are a lot of restrictions we have to ensure. This is tricky. Maybe there is a simple way to go about solving, covering all the cases here, but I don't quite follow. So if you look at this unique way to unravel way to unravel this. The final, so after some of these steps, we arrive at the part of the original board which does not have any unbroken rows or columns, and so it must be the same as in the original. So how many? So this is given by a subset of columns and a subset of rows. So how many ways can we get there? In other words, so it does not matter where this part exactly is. So let's assume that this is in the top left corner here. Okay, so no rows and no columns are unbroken. Right, so how many ways can lead us to this final step of our process? It does not look. I don't think it depends on the actual position of the rows and actual position of the columns. Why? Well, because it doesn't matter. In our construction, it never matters. It only matters how many rows we have here and how many columns we have here, I think. So we know that all of these parts, all of these. So let's look at this matrix at the 4 parts. So this is the final part. This is what's in the same rows as the final part, but we know that all of these was erased together with this row, right? So these kind of have to be of the same color, I think. Each of these short parts in each row and each column has to be of the same color, either completely white or completely black. And I don't think the... Hang on. And so the order of these rows, I don't think it matters too much. So we can just... So we're counting final like complete configurations of the complete board. It's probably hard to follow, but what we're going to do is, so we have this process, right? For each, maybe I can give an example. So let's say that, so what the process is. So let's say that we have a state like that. And so what we do is we keep track of the part, we keep track of which rows and which columns we have not yet erased. And whenever we see an unbroken row or an unbroken column, we erase it. And so we erase this, and then we erase this. And so this is the final part that we have. It does not have any unbroken rows or unbroken columns. And we know these indices here. Okay. These indices, this subset of indices, uniquely determines which part of the board is remaining. And it cannot have any unbroken rows and unbroken columns. So the question is, for this particular set, for example, 1, 2, 2, 3, if this is the same as in the original board, how many ways are there to paint everything we have removed? How many are there? But, oh, okay. No, maybe it's still all right. Yes, for different subsets, we cannot have different final configurations arriving to them from by erasing complete unbroken rows and columns. Yes. So we only ask ourselves how many ways are there to paint this remaining part that we have erased, so that it could potentially be erased by rows and columns. And this does not depend on where exactly these rows are and where exactly these columns are. It only depends on how many are there. Yeah, it appears to be the case. So that's what I was talking about here. This is the remaining part, and this is the L shape, sort of, that we have erased. So this kind of disconnects the problem from the actual board that we have, and it's about counting the configurations now, because it doesn't matter what's here, as long as it does not have unbroken rows or columns. I'm repeating myself a lot because I'm still working this out. It's not a lecture. It's like we're in this together, sort of. Right. So I think there are a few cases here. One case, so there could be a case where we've erased everything. Everything can be covered by erasing rows and columns, and so we wouldn't have these parts here. So maybe we can just count how many states we can have in the end. Like if every cell has to be colored from its initial position. What's the criterion for that? How many ways are there? We have to avoid double counting, which is pretty important. So what I want to do kind of is to, whenever we the order of the rows as we erase them is kind of, it's important, but it's not. Let's just assume that whenever we erase a row or a column from anywhere, we move it as far as possible to the right or to the left. So if we erase a black row, we move it here. If you erase a black column, if you erase a white column, we move it here. If we erase a black row, we move it here, sort of like that. Then we erase a white row, maybe. Can we do this? Okay, so here the order is somewhat important. The order is somewhat important. It's a bit tricky, isn't it? maybe we can say that whenever we can erase a white row, we erase it before the black row. Maybe that will help us. So let's try and do that. So first of all, we start by erasing everything white we can find. Okay. So this is some columns and then maybe some rows. Right. Then we erase everything black we can find. And that has to include at least one row and at least one column. Because if we, or maybe not, so if we erase a column, a black column, and there is no other black things to erase, the next is white. But there cannot be a white row here because a white column, because it could be erased before blacks here in this part, and we have to erase everything white before black. So the next is white column, which was not possible before, so that's fine. But no rows. Okay, no rows. So it's kind of, yeah, we kind of have this. We kind of have this this choice as before. So if at any stage we only erase black rows, black columns, but not black rows, then the next has to be only white rows, but no white columns. And the next cannot be black rows, I think, because for the same reason. And so only black columns are possible, and then only white rows. Hang on, how exactly does this work? Let me expand this a little bit. Okay, so here we had a black row, a black column. No black columns anymore, no black rows. No black rows. But how should this work exactly? This cannot have white columns. This cannot have white columns. So after finishing this black row, we cannot have any white columns. So we can only white rows, a few of them. And at the next stage, if we have black rows, that cannot happen because that could be erased before this. So there are only black rows again. Can this even... I don't think this is possible at all. If we start from this kind of thing, if you start from this kind of thing where white row and white column, because how does the process end like this? We should have, so we have this sequence, right? White rows, white columns, black rows, black columns, whatever. So it finishes something like this. But then let's think about it. This. So we did black row, white column, black row, white black column, white row, like black column or whatever. The last character that we erase, why didn't we erase it before? If we erased it as a white row, like we could also always erase it before this block. I think it's always true. I think this cannot happen. If we start from a configuration with white rows and white columns, then the continuation should always have both a row and a column like this, because otherwise the process cannot finish. We cannot just switch. I don't think it's possible. So it can always be rearranged into something like this, which makes this much simpler actually. Much simpler. So this is one type of configurations. So how many final configurations we have from this? So if we have so each of them can be permuted in some way. So the number of the permutations of rows and columns are kind of independent, and all of them lead to different boards, as long as we're not swapping any white columns like that. Like any equal columns that we swap, that leads to this same thing. And this can be determined, like if we take a step where we erase 2 white columns, for example, that says that, okay, this is a group of 2 equal columns. And so we have these groups. And from this we can find out the exact, yes, this is just, this is quite simple combinatorics. So basically, if this is the structure of the final board, then we take the board, we say, okay, we want to erase some whites first. We want to erase, so for example, this is a board, I don't know, 7 by 5. So we erase 3 white rows and white columns and 2 white rows. How many ways are there to do that? Well, that's 6 choose 3 times 5 choose 9. And then we have to switch to blacks and so on. Okay, so this case is simple. Now it's not. It gave me some trouble, but we've done that. Okay. And it doesn't matter if the board stays. Yes, I don't think it matters a lot if the final configuration is there or not. Yes, maybe we can forget about that sort of. Right. So what's the other case? The other case is initially we don't have this. So in the first operation, we erase either only rows or only columns. Could it be that we only erase white rows and then white columns, and then we switch to rows? If we switch to rows, then they cannot be white, right? So we can do the same picture as this again. Right, so first we erase some only the rows. Some of them are whites, some of them are blacks. For example, let's say that only whites at this point. The next are rows, which can only be black at this point. So these are only blacks. Then we can we have both black rows or columns at this point? No, because that would then we would have erased some of the, we would have a black column before, so that kind of happened. So then we have to switch to whites again, and we cannot have a white row. So whites are only columns, at least one. Then black rows, a few of them. And then again, I don't think we can finish. Because at the final stage, when we erase the final view, no, that's yes, as long as there is no final part, this kind of happen. So it's tricky. Okay, there it is. Time for another break. I'm sorry, this is such a long video, and it's like I'm having a lot of trouble thinking about these problems in front of the camera and trying to draw things out. But I try to give you an experience of how I'm solving these problems usually by myself. Right, I just need a break. Just bear with me as I go and think about this problem by myself, and I'll be back real soon. Okay, so I think I figured it out. So we did a lot of casework, and I think the way to go is to avoid all of that, all of the casework. The only thing that we need is to, so we want to start from the whole board, NM, and arrive at this unbroken part. Let's say it's height h and width y. So let's count the number of ways to get from NM to HW. So that's going to be dynamic programming. NM, HW. And then we also have to remember whether we can erase white rows, white columns, black rows, and black columns. So that's 4 bits. That's is going to be given by a mask. Okay, and so these we can do because we can just iterate how many black rows and white columns we can erase according to these restrictions. And we also naturally have that if we erase black rows, we cannot erase white columns, and vice versa. And the other condition is the other small condition is when we erase all white rows, the entirety of the board, then we also have to erase all the white columns, and vice versa. Yes, I think that's the way to go. And that gives us the mask, right? Because if we've erased white columns on one step of the process, if we erased white rows on one step of the process, let's think about that for a moment. So in this state, we have erased everything possible. So in this partial state, so we have, say we have erased some rows and some columns. If we only erased rows, we cannot erase any rows on the next step because we could have erased them before. Right, and also, but the rows that we erase on the next step can be anything, I think. And also, if we erase everything of the same color, we cannot erase the same color on the next step. But so if we only erase whites, but if we erase, but the blacks can be anything. So I think that's the key. That's the key. Yes, that's probably how it should go. And then we go back to the original board and say, okay, we apply this process to the final configuration. Either we erase everything, in which case we just have to arrive to 0, 0, or we've arrived to a partial board. And this, we just look up some other value. Right, and then there is the issue of the counting, right? The issue of the counting, and that can be arranged as well, because when we erase some rows, say we erase white rows and black rows, the number of ways to choose these white rows and black rows or columns is just binomial from the number of rows that are still available. Yes, I think that's how it should go. Very, very interesting. Yes, that's, I think so. Let's try to implement that. I hope the idea is clear. Everything that we do. All right. So max n is just the largest dimension. Let's say that it's 10. Okay, so the initial condition is given by these strings. Okay, let's not care about them for a moment. And then the dynamic programming. The dynamic programming, in fact, H and W. Yes, let's iterate over. Let's say that this is n and m of the whole board. Right. So then we iterate over where h can go. H can go between 0 and n inclusive. So that's how it goes. If one of them is a 0, the other one has to be 0 as well. So if w is equal to 0 and h is larger, then we could say that if the smallest of these is 0, but the largest of them is not 0, then this is not a configuration we're interested in. Okay, so the number of ways to arrive to this h and w, let's store them here. And this is going to be a sort of the multiplicity, sort of, right? So for each possible board that we can have at the end, each possible this reduced board, this is the number of ways to arrive to it. Right, but we also need to have the dynamic programming. Since we have fixed h and w, we don't have to introduce h and w as a parameter of the dynamic programming. Okay, so these are parts of the current board, and then this is a mask. Okay, this is the exact mask I was talking about. Which of the black and white rows and columns we can erase. We are trying to forgo the casework because it just got too complicated. Okay, so we start from n and m. Let's actually let's clear the dynamic programming between the steps. So this should be all put to 0, and then initially we start from n and m, and mask is we can't do anything, and the number of ways to arrive to this is 1. Okay, so now we go by decreasing of the current size of the board, right? Okay, so we want to go by decreasing, so let's decrease all of that, and then mask is whatever it is. All right, so in this state, just to avoid some unreachable cases, if this case is not legitimate and it cannot be reached, then let's just not do anything. Okay, so next we want to erase some black rows, black columns, white rows, white columns, and that's for cycles. So black rows, we can erase any number from 0 to I inclusive. White rows, we can erase from 0 to I minus black rows, again inclusive. And then we do the same for black columns. And then we do the same for white columns. Like that. So now let's ensure the conditions. Let us ensure the conditions. So, okay. If actually, let's say that this is, so the mask bits in mask forbid us to erase something. So the first bit, the lowest bit, forbids us to erase black rows. So if we still want to erase black rows, then this is not something we can do. The same goes for white rows. Black columns, and white columns. Right, so that ensures that we don't do anything that we are forbidden to. Next, we cannot erase black rows and white columns simultaneously. Okay. The same goes for white rows and black columns. All right. So that corresponds to all valid cases. The other invalid case is when we do not erase anything. This is not a valid move. In fact, I and J cannot be lower than H and W. So let's put that in. All right. Next, what like this is probably all valid. The other thing is if we erase all rows, for example, black rows, we can put it like that. If all rows that we erase are white, then we should also erase all white columns. And if this is not the case, then we should continue. The same goes for symmetrical configuration. Yeah, okay. Again, we are kind of ignoring, we're just putting conditions in. We don't think about what happens. It's probably going to sort itself out. And the same should go for the symmetrical case, right? Except this should be J. This should be J. This should be J. This should be J. Yes. Something like that. Okay, so this is now a valid way to do things. Right. We also need the binomials, right? So let's calculate the binomials real quick. This is simple to do. I'm not going to go into too many details, but this is how you can do it. A short way you can calculate the binomials with the Pascal's triangle. Okay. Now, there are two things we need to... So first of all, there are multiple ways of doing that. Let's say that, so this is a coefficient. What is it equal to? Out of all I rows that we have to choose black and white ones. So let's say that we choose the rows like this. Multiply that by the number of ways to choose black rows out of all these ones. Here we have to keep track of overflows, because we have to output the number model or something, and if we are not careful, we will overflow. Right, the same thing goes for black for columns. Okay, so this is our coefficient. The only other thing that we need to figure out is the new mask. What are the new constraints? And we have kind of figured this out, maybe. So if we have only erased rows, so we haven't erased any columns, then the mask should forbid us to erase the rows on the next step. So we should put bits, I think, 0 and 1. So the rows cannot happen on the next stage. The same goes for the columns. If we have not erased any rows, then we cannot erase columns on the next step. I think it goes like this. If we have only erased white ones, if we have only erased white things, so we didn't erase any blacks, then we cannot erase white things on the next step. So we have to forbid this condition here and this. So this, I think, does it. And the same if we didn't erase anything white, then we cannot erase anything black on the next step. And this is two conditions here. All right, that's probably how it goes, right? So what we now need to do is, okay, so this is not exactly true. We cannot erase the h rows that we have in the end. And so this goes, in fact, up to I minus h. This is j minus w, I think. All right, being careful here. All right, so the dynamic programming of the remaining stage of the remaining board, which is I minus all the rows that we have erased, j minus all the columns that we've erased. We should add to this number of ways to get to our current stage, and in fact there is a constraint here as well, multiplied by this coefficient here, modulo p. And we should also take this thing, modulo p. You can like retype this here, or you can do this slightly more. Actually, the most the best way I think of is like this. So this is the value that we want to update. Okay. So to this value we add things, and then we need to take it modulo p. I think that's how it works. All right. Now, after all this, we should have the answers in all of these. Like, so we need to field the multiple for h and w. And this has to be the sum of all dp's hw for different masks, because masks are not important. And then in the end we have to take this modulo p. So I think that sort of does it for computation of in how many ways we can erase things, like color things from the end. The only thing left to do is to compute the answer. And to compute the answer, we consider all possible sets of rows and columns, see if it's a legit set, if it has any unbroken rows or unbroken columns, and then add things to the answer. Okay. So let's say that R mask is the subset of the rows. C mask is the subset of the columns. We cannot have one mask empty and the other not. So if one of them is 0, the smallest is 0, but the largest is not 0, then this is not a state we're interested in. Now, if this subset is this subset good? Maybe. Let's check this. What's the time limit, by the way? 2 seconds. Maybe that's fine. Okay. So none of the rows or columns have to be unbroken, unless it's just an empty set. Okay. So we only want to do that if the set is not empty. And we have ensured that if this is not 0, then C mask is not 0 as well. Right, so how do we do that? Let's iterate over all the rows. If the row is not in the set, we are not interested in it. And then we should see which colors this row has. So has black, has white. Initially it doesn't have anything. Okay, so then we iterate over all cells in this row. If this is not in this set, we are not interested. Otherwise, if our cell here is this, then let's say that this is black, then we have black. Otherwise, we have white. All right. So now the row is unbroken if one of these two is false. So in this case, OK is false. And then we have to do the symmetrical thing on the columns. Let me indulge myself and just copy paste it here real quick with some adjustments. This is not the cleanest way to do that, but I can't be bothered at this point. Okay, so we have to swap these cycles around, then this, then this. This is fine. Okay, so in the end, if the subset that we have is not great, this is not the case that we want, and otherwise this can be the finishing state of erasing rows and columns. So we have to add the number of ways to arrive to that, and that is the multiplicity that we've counted here in this huge cycle. Reusing the same trick, we are interested in the number of bits in R mask and C mask. And that, I think, does it. It's probably not going to work, is it? We should take the answer modulo P. We should define what P is. By the way, E64 is just an alias for long. Huh, I'm lucky with compiling this time. Okay, so will it work? No. This is bad. This is all right. So let's see. Actually, let's start with a simpler example. Maybe it will fail. 3. How can you have 3 here? I don't think it's possible. No, I don't think it is. Actually, let's look at the multiplicities. So let's do some debugging here. So we can arrive at the final state in 2 different ways. We can erase everything in 2 different ways, which is correct. However, what is not correct is that clearly this considers leaving this cell without erasing anything as a valid sequence, but that is not true because it hasn't broken everything. So these conditions do not work as intended. Okay, so let's look at which R mask and C mask can possibly are considered as correct. Yes, both of them, but this can't be true, can it? Because this cannot be equal to we should skip if this bit is 0. All right. Here is the downside of the copy paste. We have to, but we can do things. When you copy paste, you have to, if you make a mistake, you have to fix it in both instances. So that's not great. Okay, 2. Since the cycles were broken, then the behavior was not what is intended. Okay. Actually, let's look at what's reachable again. Which masks are reachable? I suppose there are only 2 reachable. the entirety of the board and the small one. Yes, okay. So the number of ways to erase the entire board is not correct. It should be larger than that. Should be larger than that. All right. Huh. Yeah, it's a bit daunting to be looking at this pile of code. Oh yes, so this does not appear correct because no, this is actually fine. This is actually fine. This is only relevant when H and W are 0, so we have to erase everything. Actually, let's look at values of dynamic programming. I'm curious, especially in the case when H and W are 0. So if H is 0, output ij mask dpij mask. So that should give us a list of all the non-zero values. Yes, it's what? No, 0 to. So this bottom it doesn't refer to the same thing, does it? No, maybe it does. Okay. Oh, I see. So we could potentially erase all rows, but it would not fill in this case. Right. So it's a bit. So we have to change this a little bit. Yes, in the case when H and W is 0, it's a bit tricky because we could have 2 rows and 2 columns and erase this as black, this as white. And then in the remaining part, we kind of have 0 rows but 2 columns. So that's a special case. But we can maybe figure this out by doing this. First of all, let's make this a legitimate state. Except we cannot make any transitions from it because we have erased everything. However, we are still going to add this to the answer. Suppose this is the answer. Well, in fact, in this case, we just add something to the answer. take this model p, and then just continue, because we have erased everything. But that only works if it's 0, so it's still some cases with yes. So this we only do for the 0 case, and for the non-zero case we have to do this. We have to do this, I think. So that's slightly larger, but still not ideal. Still not ideal. What I'm wondering is why the numbers here increase. I think, yes, this should be by decreasing. All right. This is marginally better. We have passed a test case. Really good. Wasn't easy, but we did it. Let's look at this. Oh, okay, so this is tricky. If we pass this case, there is no way we can fail this problem, right? Oh, wow. Really cool. Really nice. This is a test case that checks that we haven't swapped the number of rows and columns anywhere. Nice. Did I copy that? Oh, okay, this is a big one. Yes, I think we're set. I think we got it. Maybe time limit can be an issue. Actually, let me check this real quick. If I, in the cases when it's sort of cheap to check the time limit, I try to do this before submitting. Yeah, that's fast. That's pretty fast. Okay, that's good. That's good. I think we're set. That was a tricky problem. That was a tricky problem. I think we're set. I think we're set. That took us like an hour and a half, almost. More than an hour. Yes. Yes, we've solved it. Nice. Pretty happy. That was a good practice problem. Because yes, that's like with these kind of problems, it's really hard to avoid double counting. If you try to think about not the exact states and instead the sequence of operations, if you don't do this right, you end up double counting something. And here we had to kind of really grasp the structure of how this happens by erasing rows and columns and how exactly it happens. And these can be uniquely mapped to the actual final states, right? So that's cool. I'm pretty happy. All right, so I hope that was interesting to watch, and if you try to solve this for yourself, I hope this was somewhat instructive. Maybe if you had trouble with these problems, I kind of share your pain. It wasn't really easy. Right, so I'm curious what you think about this format of videos, because it's less stressful for me compared to doing the actual contest. I used to be fine with that. Like the very first screencast used to be like really important rounds, and I was doing fine, but I cannot do this anymore. I mean, maybe I'm just getting old and stuff, but that's the breaks, I guess. All right, so let me know what you think. If you have any questions, drop them in the comments. If there are questions about my setup, like the compiler and the file manager, the editor, and what exactly do I use? What's the stuff in my template? I think some of the previous videos explained that. Like some of my videos explain the setup, and maybe some of these parts do. But yeah, if you're not comfortable with this kind of shorthands and aliases in your code, then don't use them. It will trick you. You have to have some kind of experience. Right. So I hope that was fun. I had fun. And it was a long video too, because it took my precious time. Yep. So that's it from me. Let me know what you think, and I'll see you in the next video in some next contest. Right? Bye bye.